Hey guys, just want to start by saying thanks for your patience, and I really appreciate you letting me just upload some of these instead of meeting because of all the crap I have going on this week. But again, I'll be home the rest of the afternoon, so any questions you have about this lecture video, please feel free to email me. You can kind of tell from my voice I'm a little raspy, didn't get much sleep last night, um, but I'm sure you don't want to hear all about that. So today we're talking about. And I figured I'd record my own video because I know my videos are much better than Professor Winchester's. Don't tell him I said that, but he tends to rush through things and kind of talks in a bland, monotone voice. But last class, you probably covered, we talked about 2.5. So just like in chapter one, we can have two quantities that vary proportionally to the square of another quantity. So just like in chapter one, if I had something like y is directly proportional to x, I would write y equals kx. If I had something like y is directly proportional to the square of x, you're just going to write y equals kx squared. There's nothing different except for the square now and how you solve it. Okay, so this isn't the video I posted on our Blackboard page. But if you watch that video and you're really not sure what's going on, email me. I'll just record it again myself. And I can re-explain everything to you. That's not a big deal. So we are starting 2.6, quadratic regressions. I told you this before. I just said it. Just like in chapter one, we did linear regressions. So if I had data that I knew followed somewhat of a linear path, I could use my calculator to find the quote unquote line of best fit, the line that kind of goes through the data, the middle of the data, you could say, or as close to the middle as possible. So we're doing the same thing, nothing new, except now our data is going to look a little quadratic. So it can look two ways. It could look, it's harder to draw than it looks, like an upside down U or a right side up U. So now we're going to find the quadratic of best fit, or the parabola. Oh, don't mind my hand. The parabola of best fit. The parabola that kind of goes through the center of the data. Again, the process is the same, except we're just going to hit one different button. So if you forget the process itself, here's the instructions down below, but let's go through this together. It says medicine in the bloodstream problem, very original. Quadratic regression can be used to find the mathematical model that relates the amount of ibuprofen in the bloodstream to the time since taking the pain reliever. The following data resulted from collecting blood from a volunteer and determining the amount of ibuprofen in it. So here's just our time after hours, time in hours, and here's our amount of ibuprofen in milligrams. So we're just going to take our data and plug it into our L1 and L2, just like we did in chapter one. So I'm going to go to Stat, Edit, and I'm going to clear those out. Remember, I'm going to highlight L1 and L2 and clear them out. So I have 0.5. This is the pain in the butt part, 2, 3, 4, 4.5, 135, 360, 358, 302, and 119. My data is entered, so now I'm going to go to Stat again, and then we're going to go to Calculate. So if we were in Chapter 1 and we knew this data was linear, we would use linreg. But since we're in Chapter 2 and we know this data is quadratic, we're going to use quadrag. L values come, or X values come from L1, Y values come from L2. Frequency list, we're just going to clear that out. Make sure that's empty. That should be empty. And then you're going to leave store rec, whatever. Just leave that blank as well. Hit calculate. It'll give you now, instead of just an A and a B, it'll give you an A, a B, and a C. So this is kind of a pain in the butt. We have to copy this over now. So we have our function is I with respect to T is going to be negative 61.412 T squared. I'm sorry, it's 441. 441, my bad. plus 311.77 minus 9.89. So there should be a t here, minus 9.89. So anything I want to do with this function, I have it here. So it's just like we did in the chapter 1. You can take the model and calculate future values based off the data. So again, they graph it, but you don't have to graph this in my math, I don't think. So you can just ignore that. So here's the same answer we got. So then it says find the t-intercepts and explain the meaning of these values in the context of the application. Let me copy this guy over. I don't know if I can grab the whole thing. Nope. I'll do it like this. 1 second. There we go. All right. Right. So here is our function that relates ibuprofen in the bloodstream to how many hours after you've taken it, and vice versa. And now we just want to figure out what are the t-intercepts. Remember, anytime you're looking for an intercept at all, that's going to be when the other variable equals 0. So I just want to plug in 0 for I. This whole thing's just going to become 0. And you'll see that I'm left with a quadratic equal to 0. So I can use, well, this isn't going to factor. The numbers aren't nice enough. So I have to use the quadratic formula. So what I'm going to do is I'm going to write it out, and then I'll put it in the calculator just to save a little bit of time. So this is going to be t equals negative b, negative 311.77 plus or minus the square root of b squared. These are really ugly problems, but minus 4 times a, negative 61.44 times c, which is negative 9.89, all over 2 times a, 2 times negative 61.44. Okay, it's going to be messy because this is a real world problem. Numbers aren't pretty in the real world. But I'm going to do this all in one step, okay? You can do this as well. If you have a newer 84, I'm going to do alpha y equals, enter. That'll bring up this fraction bar here. So on top, I'll have negative 311.77. I'm just going to do one of these at a time. So I have plus. No, I want to go up and over. Nope. Plus the square root of 311.77 squared minus 4 times negative 61.44 times negative 9.89, all over 2 times negative 61.44. So if you do it right, we should get 0.0319. And then all I have to do to go back and get my other answer is just highlight my original expression. I'm going to hit second left to go all the way to the left side, and then just change that plus sign to a minus sign. So I get 5.04. Okay. And what does this mean in terms of the problem? Well, after 0.0319 hours and 5.04 hours, there will be no ibuprofen in the bloodstream. Okay. So basically, these aren't exact because the data is not perfect, but this is basically there's no ibuprofen in the bloodstream before you take the medicine, and then after 5 hours, the medicine will be depleted. It will be out of your system again. So then it says find the vertex. So from last class or the class before, we know the vertex formula is negative b over 2a. That's how we're going to find the x coordinate. So this is going to be just this, negative 311.77 T, just 311.77 divided by 2 times negative 61.44. Now, when you do this in the calculator, I wouldn't try doing it all in one step because students make a lot of mistakes. So I would just figure out what the bottom is going to be first. 2 times negative 61.44. And then the top divided by that. So I get 2.537. X equals 2.537 or 2.54. And you'll see that that point is right between these two, which is what we want. Parabolas are symmetrical. So the vertex should be directly between the x-intercepts, or in this case, the t-intercepts. So now that's only half the answer. Now I need to figure out what's the y-coordinate. This is x equals this. Figure out what y is. Well, just take your x value and plug that back in for t. So we're going to just write out the whole equation, but replace x with that. Told you these are messy. Times 2.537 squared plus 311.77 times 2.537 minus 9.89. So that looks like our ibuprofen value is going to be 385.613. Now, what does that mean in terms of the problem? Well, when you have a parabola or a quadratic, the sign of the a coefficient, this sign here, determines the direction in which my parabola opens. Your parabola can open up like a cup, or it can open down like a frown. Okay? Since this is negative, our parabola is opening down like a frown. So I know that if it's opening like this, and this is the vertex, it's going to represent some maximum value. Okay? And Winchester didn't explain this in the previous video, but where the max or min occurs is the x value, or t, or whatever variables you're in. What the max or min is the y value. So shrink that. So this is saying here that the maximum amount of ibuprofen in the bloodstream occurs at 2.537 hours. The maximum amount of ibuprofen that's in the bloodstream is 385.613 milligrams. Okay, so if I want to know when or where, it's your x value. What is going to be the y value? Okay, this says the amount of ibuprofen in a patient's bloodstream cannot fall below 250 milligrams. So I don't think we have a graph up here. They were in the calculator. We're not going to do that. So we have our, I'll just rough sketch it for us. And we'll say it's roughly 0 to 5. And this is the point, our vertex, 2.537. 385.613. All right, and it wants to know how long until it falls below this line of 250 milligrams. So I'm looking for this point right here. So just like before, we're setting our equations equal to values. We're plugging values for specific variables and solving for the remaining one. So I just want to know, what is t going to be? How long until ibuprofen is 250? So I'm just going to take this equation and plug in 250. Let me rewrite that again. So we have the different color here. 250 equals negative 61.441. T squared plus 311.77 T minus 9.89, is that right? Yeah, okay. So two options here. You could subtract 250 from both sides, dive into the quadratic formula, and have at it. Okay? But you can also use the calculator to solve these problems as well. So to do that, I'm just going to plug in both equations into my y equals menu. I want to plug the right-hand side in. I'm going to plug the left-hand side in, and I should get a graph that looks like this, okay? More or less. So I'm going to plug in two equations. The first equation is going to be my model, negative 61.44 t squared, but we're going to use x because there's no t button, plus 311.77 t minus 9.89. And I'm also going to graph the line y equals 250. So then you go, all right, I'm going to hit graph, and it might show up, it might not, okay? Because your window is not set to this problem specifically. So we have to set our window to fit this image. So if you go to window, it wants to know what the smallest x value should be. Well, we know that it crosses the x-axis at 0.03, almost 0. So I'll just make that 0. We know it crosses the x-axis again a little over 5, so we'll just make that 6 just to be safe. Ignore the x scale. Y min, I know the y values are only important down to 0. And the y max, well, the highest point on my parabola is 385.613. So let's just do 390. Okay, and that should fit this picture when I hit graph. There's our parabola, and there's our line y equals 250. So I'm looking for this point right here. So I'm just going to use the calculator. I'm going to go to calculate, the blue calculate, second trace. I'm looking for the intersection of the two lines. So now it's going to say first curve and second curve, because you could have 6 or 7 things graphed here. Okay, so it wants to know which two do you want to find the intersection of. So just make sure one of them's highlighted, like this, and then make sure the other one's highlighted when it says second curve. And then it asks you to guess. I don't know why it does that. You don't have to guess. Just make sure the cursor's closer to the second intersection. So our intersection is going to be when t is 4.023. And the y value here is 250. Okay, once the intersection points between the lines, this isn't really a meaningful point, but we can find it. So I'll do the same thing, second trace, intersection. And then we're just going to do the same thing, but put the cursor closer to the left intersection. Like that. Enter, enter, enter. And this is 1.05. 250. Okay, what does that mean? Well, let me pull this up. It doesn't mean much, but technically, I guess what he wants us to say is between the hours of 1.05 and 4.023, the amount of ibuprofen in the bloodstream will be above 250 milligrams. All right. Moving right along. So let's just find the quadratic regression model that best fits. Oh, we already did this. Oh, no, VCR usage. I think there's a page missing here, isn't there? 178. Why did this not get copied over? 182. All right, let me pause this video and then I'll pull that up because I don't know what happened to it. Okay, I found it. It is the bridge problem. So it says the High Coast Bridge, or the Höga Kustenbron in Sweden, is Sweden's tallest construction. The bridge which crosses that river has its towers reaching a maximum height of 180 meters over the roadway and covers a span of 1,210 meters between the towers. The center of the suspension cable hangs 50 meters above the roadway. So translate that information into some coordinates, right? Because we can't find the model of the bridge until we have some coordinates. That's what we have to plug into the calculator. So what they're saying is that this middle line can be thought of as basically the origin of a graph, or the axes of a graph. So this is going to be my middle point, the origin, 0, 0. So I know in the middle of the bridge, the cable hangs 50 meters above the roadway. So this distance here is 50. So this coordinate right here is going to be 0, 50. All right. We need a couple more. And it says here that it has towers reaching a maximum height of 180 meters over the roadway, which spans 1,210 meters between the towers. So this is 1,210 meters. So if this is the middle, this axis here is going to be 605, half. So this point, the top of this tower, is going to be 605, 180 meters. And then just make this negative 605, 180 meters. Okay. That's enough. We only need the 3 coordinates to get the parabola, right? And since there's 3, it's actually going to go through all 3 points very nicely. So I'm just going to go back to my stat list, edit everything, clear everything out. And I'm going to plug in my x values, negative 605, 0, and positive 605. And then my y values, 180, 50. You just have to make sure they match up with the appropriate coordinate that, in the problem. Positive 180. Okay, once my data is in there, I'm going to stat, edit, quadratic regression. And we're going to hit calculate. All right, now we probably would copy this down wrong, unless I was here to let you know. But this is scientific notation, 3.55167 e to the negative 4. That basically means that we have y equals, you're going to move that decimal place 4 places to the left. So you'll have 0.0003552. That's my a coordinate. So this is going to be that times x squared. I don't think there is a b coordinate. B is going to be 0, so we don't have to write it, plus c, which is 50. Whoops, 50. Okay. And there's no b because this isn't shifted. The b really comes into play when the graph is shifted up from somewhere other than above the origin. So in this particular case, your b is going to be 0. It says an engineer needs to estimate the lengths of the vertical suspension cables that are 500 meters from the center. So he knows how high the cables go, 500 feet. This is 500 from the center of the bridge. Okay, so he wants to know the y value there. So I'm looking for the y value, and the x value is 500. So we're just going to plug that baby in. 0.0003552 times 500 squared plus 50. 138.8. Then let's just make sure that makes sense. Yep, if this is 180 here, that's believable, but that's 138, a little less than 180. Okay. Let's see what's next. I think that's the end of that chapter. So let's go. I'm going to copy one from my open math. Let's see here. No, not this. Let's do 100. I will go to the practice problems, quadratic regression models. We'll just do teacher preview. Okay, so this first one here, it just asks you, you're plugging your data. Your data for L1 is going to be days. Your data for L2 is going to be infected individuals. And then you're just going to fill in the values accordingly. But here they want you to do it first for an exponential equation. So this is weird because we don't do exponential equations until chapter 3. So we'll run through this one just so everyone knows how to do it. But I mean, again, it's the same thing. It's just you're using a different button. So we'll do number one together. So this says plug in my data. So I'm going to go to stat, edit, clear those babies out. And I'm going to plug in my X values. 1, 2. It's going to be 559, 587, 629, 670, 740, 790, 871, 931. So each of the following problems enter the regression equation values with at least 3 decimal places. So the first thing it wants is the exponential regression. We'll talk more about that in chapter 3. But just for this problem, all you have to do is go to stat, calculate, and you're going to scroll down to exponential regression. It should be option 10 or 0, depending on how you look at it. Exponential regression. X values are from L1, Y values are from L2, and I'm going to hit calculate. So I'm just going to copy these numbers over. So my A value here is 506 point, we're going to do 3 decimal places, 0.844. 506. And my B value, 1.078. Okay. It says use the model to predict the number of individuals infected with the disease after 12 days. Well, I just want to know what Y is when T is 12. So I'll take my calculator. That's going to give me 506.844 times B, which is 1.078, raised to the power of 12. We're going to enter it just like that. So we get 1248.24. 2.24, need 3 decimals, right? 244. They probably want a whole number, individuals. So they use different values than we did. So that would be that would be wrong. 1251. Because yep. So this has 3 decimal places, and they use way more. So hopefully they will give you credit for writing 1248, but I'll keep it as 1248 to see. All right, and then it says use the regression to find a linear equation that best fits the data. Linear. Same thing. We're going to go back to stat. Our data is already in there. Go to calculate, linreg, pull everything out. So this is going to be my M, in this case A, is 54.488. My B is 476.929. Yeah. Now it says use this progression to figure out the number of infected people after 12 days. Well, now this is a line. So I'm just going to fill it in like this. Y equals, so I have M, 54.488 times 12 plus 476.929. And we'll get something a little different here. So this I'm going to put in 1131. Okay. And then we're going to do it one more time with the quadratic regression. My X list is all 1. Yeah. All the way through. Okay, so my A here is going to be 3.458. B is going to be 23.363. $528.80. 804. All right, now we're just going to use that model to find the number of individuals infected after 12 days. And we're going to compare the three models and see which one makes the most sense. So I'm going to rewrite the equation. So I have 3.458 times 12 squared plus 23.363 times 12 plus 528.804. So in this model, I would get a value of 1307. So let's do 1307. So then it says, which model best fits the data? I mean, there's tests you can do to see, but by looking at these numbers, it's not really easy to tell. Like, you'd have to graph it, so we can try and graph it, but I think even the graph itself is misleading. So if I go to stat plot, I'm just going to turn that first plot on. Scatter plot from L1 and L2. I'm going to hit zoom. Nope, let's get out of there. Zoom 9 to fit the stats in the window. Zoom 9. So see, this looks pretty linear. So I would say linear is your best bet here. But if that question does pop up, I'll probably just give you full credit because I think they even have something written differently. But we're not going to talk about the mathematical way to figure this out. So they say quadratic. So I would think they were wrong. So if this question pops up, don't worry, I will fix that part of the question. Okay. And that's really it for this section. You're doing the same thing pretty much every single time. Okay. But take a look. If I look at the problem set, let's see how high we can get now. The problem set is going to be able to be done. Factor. Yeah, it looks like, I mean, you can pretty much do most of it. I think 23 and 24 might not make sense until next class, but you should be able to do up to questions 22. So give them a shot. Email me with any questions you have, anything that's not making sense. I'll get back to you as soon as possible.